under a C? Yes. I think there's actually one of those. So I think is that what it looks like? Kenzie? Okay. That softens your C, for those of you who don't take French. Right? It's been a while for me. It's been like almost 20 years. That's like crazy to say that. Right? Does it soften the C, Mackenzie?
Yeah.
Or no? You look unsure. Andrew, you take French? Good, because you're nodding your head yes with confidence, so okay. All right. So Limacons, I think is how they're said. I won't test you on that. The general format is R equals a constant A plus or minus a coefficient in front of sine or a coefficient in front of cosine. So either sine or cosine, and then a coefficient, which is going to affect amplitude of your graph, and then a plus or minus here, which is going to affect whether or not your graph is reflected, and then the A is going to be a shift up or down. So the first thing I would do for something like this, for my two-dimensional graph purposes, is rewrite it. And then graph my two-dimensional model that will bring me over to the polar graph. So rather than doing this table of values that I was doing the long way, put my midline at 1. My amplitude is still 1, but it's a negative cosine. So it's starting 1 unit below the midline, and then after a full period it will end 1 unit below the midline. Halfway through it'll reach its max, which is 1 unit above the midline, and then you have your intersections with the midline. So your critical points are any minimums, any maximums, any intersections with the midline, and any intersections or zeros, intersections with the x-axis. So this first point is, and all your points are r comma theta. So this first point is an r of 0 and a theta of 0. So this graph is starting right at the origin. And then the next point has a radius of 1 with a theta of pi over 2. So here's pi over 2, and here's 1. I wish I had like a, so hard to see in the middle there. So those graphs are like vertically on top of each other. The question is, how do I connect them? Because it's never with a straight line, right? These are quadrant 1 angles with positive radii. So to connect the first point to the second point, I'm gonna, I don't know, for lack of a better word, swirl my way through the first quadrant, right? First quadrant angles with positive radii, so it's just going to slightly curl through. However, we have to make sure that when I connect that, gosh, that's really light. I'll tell you what it looks like just here. I just did this, so you can see it. I'm not swirling through the first quadrant, and I'm never going beyond the radius of 1 in the first quadrant, because your first quadrant angles never have a radius greater than 1 in that stretch. So I need to keep that little swirl wrapped within that first circle. Yes? Okay. Then my next critical point is 2 comma pi, which is, here's pi, and then 1, 2 will put me out this way. So I'm going to continue my curling. Now, the natural continuation will bring you through the second quadrant. We can confirm that that makes sense because these are second quadrant points with positive radii. Again, as I get out there, I'm not going outside the second radius. My next critical point is 1 and then 3 pi over 2. So 3 pi over 2, 1 is right here. And when I go from the pi point to the 3 pi over 2 point. Those are quadrant 3 angles that I'm plugging in, and I get all positive radii. But again, I never go outside that third circle, or that second circle rather, because my radius maximum is 2. So that almost kind of rounds out and comes down. So after you kind of get a feel for it, you might change, smooth out your shape a little bit. And then lastly, I'm going back to 0, 2 pi, which means I'm going back to the origin. But again, almost never will a vertical, I don't need to say almost, never will a straight vertical or horizontal segment appear. It's always going to be curved. These are Q4 angles with positive radii, so naturally it brings me through the fourth quadrant anyway, but I'm looping back to the origin. And so people say that this looks like a heart shape. Agreed? So in this particular problem, it's a cosine curve. A is 1, and B is 1. And it's a minus, because it could be plus or minus. But this created what we'll call a heart shape. And you don't need to memorize these at all, but there is some interesting conversation that can happen, because not all limacons are heart-shaped. There's a heart-shaped version, and a lot of times it has to do with the magnitude of A as it compares to with B and so forth. So this particular one gives you a heart shape, but whether you know that going into it or not, you'll certainly see it once it's on your paper. Okay? Our second one, we have an electric one in the back if you want to. In the back there was just no outlet, otherwise I would have it up there. This is just your cosine curve shifted up 3 units. So 1, 2, 3 is going to put my midline here. It's a positive cosine with an amplitude of 1. So I'm starting 1 unit above the midline. I'm going to end 1 unit above the midline at 2 pi because there was no change in my period. Halfway through, I'm going to be 1 unit below the midline. And then I hit my midline halfway through each of those points. So I'm starting at point 4, 0. A theta of 0, a radius of 4. 1, 2, 3, 4. I then travel to 3 pi over 2. Okay? So when I connect those, we can agree that in that first quadrant, my radii are all between 3 and 4, correct? My radii starts at the beginning of that quadrant at 4, and then throughout that quadrant reduces to 3. So when I connect these, I'm making sure that my loop connection stays between the third and the fourth circle the entire time. Does that make sense? Okay. Next point, 2 pi. And again, when I connect these next 2 points in quadrant 2, the radii are all positive and remaining between 2 and 3. So when I connect these two, my radius is staying between the third circle and the second circle. And then my next point, 3 pi over 2, my radius is on the increase again from 2 to 3. So when I plot that point, 3 pi over 2 with a 3, it actually starts going back out again. That's my Q3. And then my Q4 brings me to 4, 2 pi, which is back to my starting point. And when I connect these with a loop, I continue to increase from a radius of 3 to a radius of 4. So this is like a circle almost, but it has a little bit of a dimple in it over here. Does that make sense? Also noticeably absent are any hits at the origin. The fact that we have no hits at the origin corresponds with what idea from the two-dimensional graph? Joey? It's up 3, and the two-dimensional graph never hits the x-axis, right? Because the two-dimensional graph never hits the x-axis, the two-dimensional graph never has a radius of 0. If you never have a radius of 0, you're never going to hit the middle. Does that make sense? The more times you hit the x-axis, the more times you hit the origin, which we'll see a lot more tomorrow when we see those rose curves. Okay, so this one, A was 3 and B was 1. This ended up being a dimple. Because your shift was greater than your amplitude, really, you end up having a kind of a circle-like thing that never really retreats back to the origin at all, creating a dimple as opposed to creating a heart shape that does come to a point at the origin. Okay? On the back, I'd rewrite this as 2 sine theta plus 1. Midline at 1. We're going to start on the midline and end on the midline for our sine curve. And we have a halfway point at pi on the midline as well, with an amplitude of 2. So in this case, our amplitude, our A value, oh no, A is 1, B is 2. But our amplitude is bigger than our vertical shift, which, because our amplitude is 2, we're going to go up above the midline by 2. That doesn't create anything additional. But when we go below the midline by 2, what happens is we've created 2 more critical points than we've had in the previous problems, right? Because your critical points are minimums and maximums. We still have those. Anytime you hit the midline, and also anytime you hit the x-axis, because hitting the x-axis equates to hitting the origin. Yeah. Did I? I did. Thank you. It looked a little pointy. I did notice that. There we go. Thank you. So we have the same 5 critical points that we always have, but an additional 2 added onto there because we've actually hit the x-axis, which is hitting the origin. We hit the x-axis before, but it was also at the minimum, so it didn't create anything additional. These hit the x-axis in between. So we'll still go through our points starting at 1, 0, theta of 0, radius of 1, and then radius of 3, theta of pi over 2. And we'll connect those staying between the first. And that's as high as the radius is ever going to get, so we can imagine that this is going to start to retreat back in to smaller radii. Next critical point is 1 pi. So far, so good. That puts us through those first 3. And then very shortly after that, we get to something with a radius of 0. So 0, comma, some angle I don't necessarily know. What I do know is that that angle, this little stretch, is in which quadrant? beyond pi prior to 3 pi over 2 is in what quadrant? Quadrant 3. And these quadrant 3 angles, the first initial part of quadrant 3 anyway, has positive radii. So that's where the continuation of the graph is going to take you anyway, but this needs to stay within the third quadrant really briefly till it gets back to the origin. So my next critical point is the origin, and it's just a really small little loop to get me there between those 2 points. And then my next, and I don't really know what angle that's happening at. I don't really need to know because it's at the origin regardless. But then my next critical point is -1, 3 pi over 2, which 3 pi over 2 is down here. -1 of that would be up here. And now we're trying to connect the origin with that very next point. Again, the natural continuation is going to loop you through which quadrant? If I come around and I end it at the origin, but I need to get here, which quadrant am I going to go into briefly? The first, right? You never like do a sudden change and go back into the second. I'm coming around counterclockwise. I'm going to continue to come around counterclockwise, and I'm going to sweep really briefly here into the first quadrant, which should make sense. Go over here to your two-dimensional graph. We're still plugging in third quadrant angles, but with negative radii all of a sudden, right? Third quadrants with negative radii swings you back into quadrant 1. So there's a teeny tiny little loop through the first quadrant connecting those 2 points. My next critical point is back at the origin again. 0, some angle I don't know and I don't care about. But again, if I now need to, I just left off up here and I need to go back to the origin. Again, my natural continuation in counterclockwise motion is going to bring me in and through quadrant 3 to loop back around to the origin. Which puts me through quadrant 2. Why should that make sense? Because I'm plugging in quadrant 4 angles with negative radii. Quadrant 4 angles with negative radii brings me through quadrant 2. And then the last little stretch I need to do to get to 1, 2 pi, which is where my graph started, still quadrant 4 angles, and this last little sliver of it does have positive radii in the fourth quadrant, so it will continue, as the graph would bring you anyway, it will continue to bring you back really small loop through quadrant 4. So without being on the paper that it's hard to see, this graph started at 2. No, it didn't. 1. Went out to 2. Came back into 1. Went through the origin and kind of looped around. Yes? Something like that. Where that's your origin. Good? So an inner loop. That happened because we had a few additional trips to the x-axis, which equated to those additional trips to the origin, which gives us looping. Okay? We would say that this is an inner loop. And really, again, you don't have to memorize this, but you can make sense of it, I think. It's the fact that your amplitude was greater than your vertical shift was. It wasn't exactly equal to it, it actually surpassed it, so it created those extra points. Any questions? Okay, and your last one. I'm going to do -2 sine theta plus 3. So here, our phase shift is up 3. not a phase shift. I shouldn't have said that. Vertical shift. Our amplitude is 2. So if you shift this up 3 and your amplitude is 2, are you going to hit the x-axis at all? No, right? And you'll see that more as we get this together. I'll put a midline at 3. I'm going to go off the graph a little bit anymore. I'd probably rescale, but vertical or horizontal asymptote at 3, and then it's a sine graph, so it's starting at 0, ending on the midline, halfway point on the midline, but it's a negative sign, so it's going to go down 2 first to its minimum. And see, that amplitude of down 2 was not enough to get us to the x-axis. This graph's never going to therefore hit the origin. And then over here we go up 2, and this is where I'm slightly off the graph. Anymore I would have had to rescale. So we have r theta, and our very first point is an r of 3 and a theta of 0. So my graph starts out there. My very next point is radius of 1, theta of pi over 2. My very next point is a radius of 3, theta of pi. And then we have radius of 5 and theta of 3 pi over 2. And then back to the beginning, which is 3 as your radius and 2 pi. This almost looks like a dimple as well. Little less circular than our other dimple was, though. And that's just because with such a big shift, your maximum is such a different magnitude of 5 than your minimum just has a magnitude of 1. On that side, we only go out like a radius of 1, but then it really increases to a radius of 5 down on the other side. Does that make sense? Okay, so now that you've seen that, I'm going to show you the chart that I initially So here's all your different formats. Obviously you can do a plus the b sine or a minus the b of sine. A plus the b of cosine, a minus the b of cosine. A always has to be greater than 0, which means limacons always have a vertical shift of some sort, right? A change in the midline. And the b means they always have an amplitude. Well, it's greater than 0, so I guess that makes sense. You have to have some number, not 0. The plus and minus is kind of taken care of separately. So it's really, these are the rules you don't have to memorize, but it's all about the ratio of your vertical shift to your amplitude. And if that ratio was less than 1, we get that inner loop. That's because the vertical shift is smaller than the amplitude change. So we actually hit a 0 additional times. Then we have a heart-shaped, which it really comes back to the origin at a point and goes right out. And then we have a dimple with no inner loop. And I guess that circle one, that first one we did, which exercise was that? That would have been this one, I believe, right? Because A was 3 and B was 1. So an A of 3 and a B of 1, 3 over 1 would be 3. If that ratio is greater than 2, they're not calling it a dimple. They're just kind of flattening the side of it. Does that make sense? It doesn't matter. You're not going to be called on dimples and inner loops and heart shape, but it's just worth noting that it's how these vertical shifts compare to the amplitude that creates different ideas. All circular, but it's whether or not it's like a flattened circle, a dimpled circle, a heart-shaped circle, and a looping circle that changes. Okie doke. Any questions? All right. So we will stop there. Your homework is page 666